ezRA, or Easy Radio Astronomy, or I call it ezRA, is a package of software and perhaps some hardware hints to make 1420 megahertz galactic hydrogen data collection and analysis, receiving that from the sky and seeing what we can learn from it. It's available for free on GitHub under my name, Ted Klein /ezRA. Go check it out. Easy Radio Astronomy is largely a summary of my exploration of radio astronomy. It started about 3.5 years ago in August of 2019 when I was told about a radio dish up at the Estes Park Memorial Observatory in Estes Park, Colorado. The high school students, along with an energetic science teacher, had created and built a dish, a 10-foot radio dish, to observe 1420 megahertz galactic hydrogen signals from the sky. It sort of worked. The radio part worked okay. They didn't quite know what to do with it, but they had troubles with the computer controlling the motors. By this time, 5 years later, the teacher had left and all the students had graduated, so nobody knew anything about it. I was lucky and figured out a way to make it work. And so suddenly I had a working dish. What do I do with it? I found the MIT Haystack SRT program, which is Small Radio Telescope, and it got it to work just fine. So now I had signals. What do I do with the signals? And that's kind of the beginning of Easy Radio Astronomy software. Looking here at my cursor up in the top left, you can see an antenna. That's real hardware talking to a coax cable that runs to a radio. That's real hardware that is controlled by a whole bunch of software down below. The top row is a whole bunch of examples of ways to control that radio. I've recently written ezCol, COL for collect, to control the radio. But before that, there were lots of other things. Very popular is SDR Sharp from airspy.com. And there is an IF average plugin that you can add that collects the data, provides a nice spectrum, and writes it to a data file. I said I was using MIT's Haystack SRT program running on Linux, and that was writing data files. The British Astronomical Association has a YouTube channel, and Marcus at the Canadian Centre for Experimental Radio Astronomy has a nice video where he describes another program using GNU Radio to write data files, collecting after controlling the radio. There is a hardware company that used to produce boxes that took in 1420 megahertz radio energy and convert it to a serial port out the back to talk to a PC that could write data files. Parac.edu has a program with CFRAD2 that writes data files. Up on GitHub, there is a program called H-Line, H-line, that nicely writes data files. On pypi.org, there are lots of projects, including one called Virgo, Astro minus Virgo, you might look for, that writes data files. The West Virginia University, with its Radio Astronomy Instrumentation Laboratory, has a program to make homemade horn antennas and process radio signals from the sky. That's at WVURAIL.org. So we got lots of different kinds of data files. I've made a format called ezRA.txt data files. EasyCol knows how to write to those directly. And I have written converters for several of these others, including SpectraCyber, that convert into that minimal format. What would that minimal format be? What's the smallest amount that you could collect that would be useful just to make the files smaller? I think we need to collect the telescope details, like the telescope name, where the telescope is on the Earth, that would be the latitude, longitude, and the altitude above mean sea level. How about the telescope bearing? When you're taking the readings, where is the telescope pointing? Think of it as a large military cannon. Are you pointing it to the north at 0 degrees azimuth? Or are you pointing it to the east at 90 degrees azimuth? Or perhaps more commonly, pointing it straight south 180 degrees azimuth? And then where's the cannon pointed? Is it pointed at the horizon at 0 degrees? Is your telescope pointed halfway up, maybe at 45 degrees? Or is it pointing straight up at 90 degrees? It could even be bending over backwards all the way to an elevation of 180 degrees. And for every data sample, what's the smallest amount that we could collect just to make the file small and fast? We want to record the time quite precisely. And we want to remember the spectrum of a power spectrum. For a whole bunch of frequencies, what is the power received during that sample time? And then there might be other different information on the end, data types. Was the data received horizontally polarized? Was it vertically polarized? Was it circularly polarized? And there are two types, clockwise and anti-clockwise, counterclockwise. Was it from antenna A, or did you use other amplifiers? And was it from antenna B? Was it from a special reference signal that we should learn about later? So all those data types could be recorded just by a single character put at the end of the data. And then let's write it into a text file so we can read it easily, make it human readable, and try to reduce the characters where we can. What is that file going to look like? It's going to record a whole bunch of information. I said the power for several different frequencies. Here's 256 different frequencies, each represented by a little red dot making a curve. The curve starts out at low frequencies with low energy. And when it ends up at high frequencies, it has low energy. But in the meantime, it's got this funny curvy shape, 3 different humps, that is a characteristic of the electronics involved. There are amplifiers and filters, and even the radio itself has an electronic signature to it. And it gives some kind of characteristic shape. We can remove that shape later on. If the radio is a software-defined radio, an SDR, it often has a little spike right on the center frequency, which is a characteristic of how the SDR works. It's just kind of a math error. We can remove that spike later as well. But along with that, sometimes there's a funny little bump up here that we receive in the energy from the sky. Sometimes that bump is on the left, sometimes it's at a higher frequency on the right. It's different shapes. It depends on where you're looking at the sky and perhaps what time of year. I say that's a sign of galactic hydrogen. Hydrogen atoms way out in the plane of the galaxy, or perhaps above and below. spontaneously lowering their energy state and spitting out a little bit of energy. And if it happens to come down to Earth, to your antenna, and your antenna is looking the right way, you collect that energy. There are so many hydrogen atoms up there in space that the energy continues all the time. All we got to do is look up and look at different parts of the sky and collect that energy. Here's what the data file actually looks like. Holy cow, what a mess of numbers. It starts off with some kind of header. We'll look at that more closely in bigger type. And then it seems to have almost paragraphs. They're actually one long line that just wraps around forever. Another long line, and another one. Each one of those long lines is a sample. I defined the very first sample as sample 0. The next one long line is sample 1. The next line after that is sample 2. There are 256, there's a timestamp in the beginning, we'll talk about that. And then there are 256 numbers representing the energy for each one of those 256 frequencies in each sample. And there might be even a little character at the end or not on each sample. Let's take a look at those more closely by zooming in up here, the top left. Here's the same text, but I've taken out 252 of those numbers in each sample, just so it fits on the page here. Each file starts out with certain characters. It needs to start out with the word from and 5 characters, EZ call for collect. In this case, it actually has EZ call and the name of the version of the program involved. 23 is the last 2 digits of 2023, the year. 02 must be the month, February. 08 is the day. There was one revision A, and this is a Python program, so it must end in .py. That's the name of the program that collected it. One time we need to know where the telescope is. It's on Earth at a certain latitude and at a certain longitude. The minus sign means it's west of London. Above mean sea level is recorded in meters. And there's a name on the end. You'll see this a lot. This is my ham radio call sign, November 0, Romeo, Quebec, Victor. And I have an 8-foot dish in my backyard that we're using here. There's one time we need to record all the frequencies. What's the lowest frequency of all those frequency channels? What's the highest frequency of all those channels? And how many of those channels are there? How many frequency bins? How many frequency channels? How many frequency buckets? How many frequency bins? Or short, we call it freak bin. How many? In this case, it's 256. It could be any power of 2, probably above that. 512, 1024, 2048 are popular. And at least at the beginning, you got to tell me where the telescope is pointed. In this case, it's 180 degrees and pointing straight up at 90. These two numbers can have a decimal digit as well. This next this line with as-L can be entered during the data following in case the telescope moves. The next line is a comment because it starts with a pound sign. It just reminds everyone all the times are measured in UTC, Universal Time Coordinate, the way the French say it. In English, we call it Coordinated Universal Time, which is largely London time if we ignore all the daylight saving changes. When this was recorded, the SDR said the gain was 49.6, so I wrote it in the file as a comment. And then this last comment talks about, just reminds us that all the numbers following are power measurements, not voltage. Then there's samples, lots of them. In this case, there are about 900 of them. There can be thousands and more. Each one is a very long line. It starts with this kind of time format. Here's the year, the month, and the day, followed by a T, then the hours, minutes, and seconds. The seconds can have decimal points if you wish, of universal in UTC time, followed by, it said 256 numbers. Those are all the values for those different frequency channels. And then maybe followed by a character like R for reference in this case. The next sample is the same, but with different numbers, but it has no letter after it. That must mean it's coming directly from the antenna itself. Here's another sample, and it's got an R after it for reference. The next one has no character at the end, so it must be directly from the antenna. And here's another R, so alternating back and forth, and it goes on forever. Lots and lots of samples. Hooray. So now we got all this radio information in a file. This should be easy. Let's pull up a spreadsheet program, much like Microsoft Excel, or maybe the free LibreOffice Calc, and see what it says. We should be able to parse that information and draw some graphs. That's what the next video is all about. See you at the next video.